Nuclear weapons operate on the principles of nuclear reactions. There are two types of nuclear reactions that can power these weapons: fission and fusion. Fission involves splitting heavy atoms like uranium or plutonium. When the nucleus splits, it releases energy and neutrons. Fusion, on the other hand, involves combining light atoms like hydrogen. This process also releases substantial energy. These nuclear reactions release enormous amounts of energy according to Einstein's famous equation, E equals mc squared. This equation shows that even a small amount of mass can be converted into an enormous amount of energy. The c-squared term represents the speed of light multiplied by itself, which is a very large number. This fundamental concept is what makes nuclear weapons thousands of times more powerful than conventional explosives of similar size. Fission bombs represent the first generation of nuclear weapons technology. These weapons, like those used in Hiroshima and Nagasaki in 1945, work by splitting heavy atoms such as uranium-235 or plutonium-239. The process begins when a neutron strikes these heavy, unstable atoms. When struck, these atoms split and release energy along with more neutrons, creating what's known as a chain reaction. In a chain reaction, neutrons released from splitting atoms go on to split more atoms, releasing more neutrons and energy. This reaction begins with a single atom splitting. Then, those neutrons trigger more atoms to split, which release even more neutrons. This rapidly multiplies, creating an explosive chain reaction that releases enormous energy. This reaction becomes explosive when it reaches critical mass, the minimum amount of fissile material needed to sustain the chain reaction. In a subcritical mass, most neutrons escape before causing more fissions. But in a critical mass, enough neutrons remain inside to create a sustained reaction. The bomb design uses conventional explosives to compress fissile material to critical mass. When detonated, these explosives rapidly compress the fissile material, increasing its density beyond critical mass and initiating a nuclear explosion. The gun-type design is the simplest nuclear weapon design used in the little boy bomb dropped on Hiroshima in 1945. This design works by using conventional explosives to fire one piece of uranium-235 into another at high speed. When detonated, the explosive propels the projectile down a barrel, slamming it into the target piece. When the two subcritical pieces combine, they form a supercritical mass. This triggers a nuclear chain reaction, releasing enormous energy. The gun-type design has significant limitations. It can only be used with uranium-235. If plutonium were used instead, spontaneous fission would cause a premature chain reaction, resulting in a fissile, a partial detonation with greatly reduced yield. This design is relatively inefficient, using more fissile material than necessary. However, its simplicity made it extremely reliable. The little boy bomb was so reliable that it was deployed without a full-scale test. Because of these limitations, more advanced nuclear weapon designs were developed, such as the implosion design, which could work efficiently with plutonium. The implosion design represents a more advanced approach to fission weapons compared to the gun-type design. The implosion design was used in the Fat Man bomb dropped on Nagasaki in August 1945. Unlike the gun-type design, the implosion design surrounds a subcritical plutonium core with precisely shaped conventional explosives. When these explosives detonate simultaneously, they create an inward pressure wave that compresses the plutonium core. This compression increases the density of the plutonium, bringing it to a supercritical state. A neutron initiator at the center releases neutrons at the moment of maximum compression. These neutrons trigger the chain reaction at precisely the optimal moment of compression, maximizing the efficiency of the nuclear material. The implosion design offers several advantages over the simpler gun-type design, including more efficient use of fissile material and the ability to use plutonium. However, these benefits come with significant technical challenges that require precise engineering and timing. Thermonuclear weapons, also known as hydrogen bombs, represent a significant advancement in nuclear weapon technology. Unlike pure fission bombs, these weapons use a two-stage design that combines fission and fusion processes. A fission bomb serves as the primary stage, generating the extreme heat and pressure needed to trigger the fusion's secondary stage. The fusion stage involves hydrogen isotopes, specifically deuterium and tritium, which are forced to combine under extreme conditions. When these isotopes fuse together, they form helium while releasing an enormous amount of energy, significantly more than fission alone. This two-stage design allows thermonuclear weapons to achieve much higher explosive yields compared to pure fission bombs. While fission bombs typically yield around 20 kilotons of TNT equivalent, thermonuclear designs can range from hundreds of kilotons to many megatons, with a theoretical unlimited explosive power. The Teller-Ulam design represents the foundation of modern thermonuclear weapons. This two-stage design begins with a primary stage, essentially a fission bomb similar to the implosion design we discussed earlier. The secondary stage contains thermonuclear fusion fuel, typically lithium deuteride. When the primary fission bomb detonates, it releases an enormous amount of energy in the form of X-rays. These X-rays are channeled between the device casing and a radiation shield, creating a plasma that surrounds the secondary stage. This intense X-ray pressure compresses the secondary stage dramatically, raising internal temperatures to tens of millions of degrees. Under these extreme conditions of temperature and pressure, fusion reactions begin in the secondary stage. Surrounding the fusion fuel is a uranium tamper, which serves multiple critical functions. First, it helps reflect radiation inward, enhancing compression of the fusion fuel. Second, it prevents the fuel from expanding too rapidly, extending the fusion reaction time. What makes the Teller-Ulam design so powerful is its fission-fusion-fission process. The process begins with the primary fission stage detonating. This generates X-rays that compress the secondary fusion stage. Fusion reactions then begin in the compressed secondary. Finally, the neutrons produced by the fusion reactions cause fast fission in the uranium tamper, significantly boosting the weapon's overall yield. This elegant but devastating design enabled the creation of thermonuclear weapons with yields hundreds or even thousands of times greater than the first atomic bombs. Nuclear weapons are categorized by their explosive yield and destructive effects. Nuclear weapon power is measured in equivalent tons of TNT, from kilotons to megatons. The scale ranges from tactical weapons of just 100 tons to the Hiroshima bomb at 15 kilotons, up to the largest tested weapon, the Tsar Bomba, at 50 megatons. Nuclear detonations produce three immediate and devastating effects. First, thermal radiation creates an intense flash and fireball with temperatures reaching millions of degrees, vaporizing everything nearby. Second, a powerful blast wave expands outward, destroying buildings miles from the detonation point. Third, prompt radiation releases neutrons and gamma rays that cause acute radiation sickness or death. The radius and intensity of these effects scale with the weapon's yield. For a 1 megaton weapon, lethal radiation extends about 1 mile, while building-destroying blast waves reach 3 miles from the epicenter. Third-degree burns from thermal radiation can occur up to 5 miles away. Initial radiation bursts occur within the first minute, while fallout effects continue much longer. Each tenfold increase in yield, such as from 1 to 10 megatons, increases the damage radius by approximately 3 times. Section 8. Fallout and long-term effects. After a nuclear detonation, radioactive particles are drawn up into the mushroom cloud. These particles can be carried by wind for hundreds of miles. Radioactive fallout poses serious health risks to humans. When fallout settles on surfaces, it can cause radiation sickness. Symptoms of radiation exposure include nausea, vomiting, hair loss, infections, and internal bleeding. Long-term exposure increases cancer risk significantly. Radioactive fallout has severe environmental impacts. Radioactive particles settle on the ground and contaminate soil. Over time, these contaminants can leach into groundwater systems, affecting drinking water supplies and aquatic ecosystems. High-altitude nuclear detonations produce a powerful electromagnetic pulse, or EMP. This pulse radiates outward and can affect an area of hundreds of kilometers. The EMP can disable electronic equipment across vast areas, including power grids, communications, and computers. To summarize, nuclear fallout presents multiple severe hazards that persist long after detonation. These long-term effects make nuclear weapons particularly devastating beyond their immediate blast damage. International efforts have been established to prevent the spread of nuclear weapons due to their destructive power. The Nuclear Non-Proliferation Treaty, or NPT, is the cornerstone of global efforts to prevent the spread of nuclear weapons. It rests on three main pillars: preventing the spread of nuclear weapons, promoting disarmament, and facilitating peaceful use of nuclear technology. Several treaties have banned nuclear testing in various environments. The Partial Test Ban Treaty of 1963 prohibited atmospheric, underwater, and outer space tests. The Comprehensive Test Ban Treaty of 1996 aims to ban all nuclear explosions in all environments. These treaties are supported by sophisticated monitoring systems that can detect nuclear explosions anywhere in the world, including seismic stations, atmospheric monitoring, and international inspections. Arms reduction treaties between the United States and Russia have significantly reduced global nuclear stockpiles from Cold War peaks. The START I Treaty of 1991 limited each country to 6,000 strategic nuclear warheads, while the New START Treaty of 2010 further reduced this limit to 1,550 deployed warheads. This graph shows how global nuclear stockpiles peaked at about 65,000 warheads in 1986 during the Cold War, and have since decreased to approximately 12,500 warheads today, largely due to these arms control agreements. One of the biggest challenges in non-proliferation is the dual-use nature of nuclear technology. The same basic scientific principles and technologies that enable peaceful applications like nuclear power can also be repurposed for weapons development. Despite significant progress in nuclear non-proliferation efforts, several challenges remain. These include ensuring compliance with existing treaties, preventing nuclear terrorism, managing new proliferation risks, and balancing countries' energy needs with global security concerns.